Good morning. Thank you for having me here today. My name is Tomasz Jakóbiec. I represent Rockwell Automation. And my talk today is entitled In the Search for Evolutionary Architecture and How to Improve the Legacy Code. But before I will jump to the main topic, I would like to make a small disclaimer. Let me use the Isaac Newton words that if I have seen further than others, it's by standing on the shoulders of the giants. I'm pretty sure that Newton means something different than I try to say, but what I'm trying to say is that we shall pay respect to the legacy code and legacy code creators. After all, in most cases, it puts food on the table, so generally brings a revenue to the company we work in. And we as an organization would never be in the place where we are right now without these previous efforts. And saying that, I think we can move and start to complain about the legacy code. And first of all, I would like to start with and talk about the importance of the software architecture. And let's see what the bad choices or maybe lack of the right choices about the code structure can do to our software. I will picture that with a real case study. At least R.C. Martin in his Clean Architecture books claims that it's a real case study. And let's see what we have on this chart. This is size of engineering team that were hired and was working on some business software. And what we see here is that the number of developers that work on the software grow up quite rapidly, starting with the 5th release. So what we can say about this situation? For sure, such huge number of developers hired to work on some software mean that a lot of new functionality have to be delivered with these next releases. So for sure, the customer shall be pretty happy with this new functionality, and happy customers mean the cash shall flow to the organization, to the company, and also to the packets of developers. So generally, it's a big success story. To answer that question, is it success or not, we have to take a look on two more graphs, two more charts, and one on the left present as a product size in the number of thousands of code lines. And what we see is quite strange because the code base starts to grow up, I think, with the 3rd release. There is not much progress considering the next releases. So if we think about how many developers were hired to work on this product, which we saw on the previous diagram, and there is not much new functionality that delivered with the next releases, then there is no surprise when we take a look on this diagram, which shows us cost per code line, and we see that this costs are skyrocketing here. So it's not a success. I would say it's some kind of disaster. I even call it calamity. So the question is, where are we right now? And I would say that as a result of poor choices or perhaps lack of the right choices about the code structure, the structure of this code that this company had is full of unattended dependencies between the classes and modules that generally confuses developers. And if we ask ChatGPT, which somehow is a common knowledge, why confusing developers with the not correct code structure is a bad thing, it will tell us, among others, that it's never a good thing confusing developers with that, because of course it is hard to implement a new functionality without the introducing regression in the old functionality. It's hard to test such code, and it's generally hard to collaborate on such code base between the teams, and sometimes even between single developers. And as a result, what we have is that everything takes more time, to be done, and the company is lagging behind the competitors and may even lose the market and go out of the business, and things like that happened in the past. So another question is how I'm so sure of that. I'm so sure of that because we saw in our organization a very similar problem. And this heart of darkness, this diagram here, presents dependencies between the classes and modules in one of our legacy code. We call this dependency between the classes in the books architectural coupling. And if this word architecture was spoken, then let's try to talk about what is the software architecture. Considering what we saw in this previous example, looks like the software architecture is all these things that are hard to change later. But frankly speaking, it's not proper definition of the software architecture. But I would like to ask you guys to remember word change. We will need this word later. So, what is the proper definition of the software architecture? The proper definition by the books is like that. It's a set of important project-related decision that shapes the software structure in a way that software supports selected quality attributes. I will talk about these quality attributes later, and other properties. And all these decisions shall reduce the number of people needed to create and maintain the software. What is interesting to note at this moment that software architecture has limited impact on the functionality. Because one may imagine a software that is shaped like a big ball of mud, or some other call it a spaghetti code, but it still does the job as required. But the question is it easy to maintain? Is it easy to debug? Is it easy to extend? Is it easy to port to different platforms? That are the questions that shall interest us. Returning to these quality attributes, of course, there are some definitions by the book, but I think the few examples will give us better insight what are these quality attributes. The quality attributes are all these abilities like scalability, security, reliability, availability, testability. All these abilities that are important if we consider the long term of code use. The question is if there are any other factors that impact the software architecture, and yes, of course there are. For example, on top of quality attributes, we may have some constraints, some business constraints. For example, we have some limited budget to do our software solution. Of course, there are also functional requirements that will impact the architecture. Let's imagine that our solution needs to store some data. So perhaps we shall consider within our architecture some kind of database engine to hold this data. There are also other things like architectural rules. For example, you will never mix the code that does the user interface with the business rules implementation. That's a generic rules that everybody shall know. Then there are some technology has some impact on our software architecture. Then architect skills and knowledge, and also team skills and teams organization. What is important to say at this moment, that all these factors, I mentioned before, may change and mostly will change with time. So the point is the software architecture shall support the change. That's why I needed this word change before. So maybe not just react to the change, but in fact embrace this change and continuously grow to accommodate this change. I know that it sounds like a bunch of buzzwords, which is easy to say, but the question is how to do this. It's quite more complicated. So I think this evolutionary architecture concept came to the rescue. This concept is well described in this Neil Force and his colleagues' books, Building Evolutionary Architectures. And by this book, the definition is like that. An evolutionary architecture approach support guided incremental change across multiple dimensions, which are quality attributes we mentioned before, functional requirements, architectural rules, constraint, architectural couplings, technical aspect, etc. So I like to add that this concept, this evolutionary architecture stands on 4 pillars, which are, first one, guided and incremental change. Second pillar are fitness functions. Third one, correct architectural coupling. And fourth one, correct data coupling. And let me use a real-life example to illustrate this, how it works. Let's imagine that there is a company that produces the automation devices, and they are producing some kind of network devices also used within automation systems. And to do this network things, we need to have a bunch of source code sources that will organize as network communication. So we need to have some network communication stack, which is a bunch of source files that do the networking. And we are using this hypothetical company is using these sources, this network communication stack, on multiple network devices to create, develop multiple network devices. What we know from the business context of this organization, that all devices have different network capabilities and also different network needs. And company is releasing new network devices every single year. And what we know also that every single year there is a need to push more and more data over the network. That's requested by customers. So let's try to come up with some quality attributes that may be needed for such kind of software, for such kind of communication stack. For sure, testability. We'd like to test code as soon as possible, as early as it's possible. And this kind of quality attribute is very universal and is generally applies for every single software we can imagine. Then if we talk about the network communication have to happen according to some standards, according to some protocols. So for sure, the network standard compatibility is important quality factor for us. Then performance. We would like to push more and more data over the network, so generally the software shall have high performance. And then I mentioned that every year we're developing new devices, different devices, so we would like to reuse this code and also configure it in the way that will satisfy different devices and different needs. And then I mentioned that the expectation from the market are higher and higher every year. More and more data have to be pushed over the network, so we may need to switch from one CPU from one hardware to another hardware to accommodate to this need. Just have a faster CPU. So we need to port this code to some other hardware platform. So portability is important quality attribute for us. So let's take a look on the first pillar of this evolutionary architecture, which is guided incremental and iterative change. First of all, we have to understand that there must be a vision of the future architecture, not a current architecture of our code, but this what we would like to have in the future architecture that supports these quality attributes we just mentioned a few seconds before. And as a result of this future architecture that we will have to come up, we will have some architectural rules that will guide our changes. As I mentioned, for example, we will never mix the code that does the user interface and business rules together in one file on one class. That's one of these architectural rules. So these changes that we would like to do with our legacy code have to be planned and executed step by step, for example, sprint by sprint. And we may just assign a percentage of agile teams' capacity to do these changes. But the question at this moment is, if we do these changes step by step, sprint by step, are we going in the right direction? We need to have some kind of compass that will guide us. And yes, there is something like that, and we call it a fitness functions. Sorry, guys. that examines the correctness of our code changes. So let's see what are these fitness functions. I like to call them a second pillar of the evolutionary architecture. And by the book, the definition is: an architectural fitness function provides an objective integrity assessment of some quality attributes and other factors. So let's use some common language to describe this. Let's imagine that this fitness function is some kind of black box thing that takes as the input two other things: source code, or maybe executable code. That's one input to this black box. And second input is a quality attribute or other factor we would like to consider. And then this magical black box do something and return us results to tell us how well we support such quality attribute. So two examples maybe help us to understand it better. Let's imagine that I have an executable code that runs on some CPU. And then I have quality attribute, which is called a performance, defined somehow. And in this case, my black box, my fitness function is nothing else than performance benchmark that measures this performance and gives us a number, how many packets per second we can push over the network. And in this case, the fitness function is just a performance benchmark. Another one example. This time, to our black box, we take a source code and some files which defines the required order of dependencies between the classes in our project. And then what this black box do, what this fitness function do, it just runs some kind of code checker, dependency code checker, which produce us a graphs with dependencies between the classes, which have colored arrows, which present us correct and not correct associations between the classes, and then also some metrics, some numbers, which tell us how many relation between the classes are correct and how much is not correct. So this is another one example of fitness function, which in this case is source code dependency checker, and it could be different kind of things to be checked with these fitness functions. What is important to say that we shall never optimize our software architecture against one fitness function. So let's imagine that we have only benchmark. So we can end up with any code untangled as we would like to have, some really spaghetti code, which is still quite fast. So we shall never use only one fitness function. We shall use a number of fitness functions. So we need to have some kind of system-wide approach. I like to call it, we need a holistic fitness function that considers multiple other smaller fitness functions. And this is exactly what we have in Rockwell on our continuous integration environment, on our Jenkins. So we have fitness functions which are very typical things. For example, unit test or integration test, some open box tests. We have some closed box tests, which are some kind of smoke test, sanity test, and also benchmarks. And then we have this open box metrics. So this architectural metrics that measures, for example, a code cyclomatic complexity. So no one is able to write too complicated, too long, too wide function or methods. Or also code dependency / architectural coupling checkers. And only when all these functions, all these fitness functions are satisfied with the delivery, then and only then one can deliver the changes to the main branch. So if you not satisfy one of these fitness functions, then you will not deliver the changes. So, third pillar of evolutionary architecture, architectural coupling. As we learn by this set example with this thing, not attending dependencies between the modules and classes causes major problem of the software. And this thing is nothing new. It's well defined and well known and described in the books. And this kind of thing is also called in the book as monolith anti-pattern. Personally, I like to call it a chaotic monolith, not just a monolith, because mostly in books, this monolith is described and pictured that way. But unfortunately, in real life, it looks rather that way. So generally, we need to do something with that. We need to some kind of split it. We need to some kind organize it. So how we can split the code? In general, there are two ways of splitting the code. First way is called a technical split. And most explicit example of the technical split is something that is called a layered architectural pattern. I think everybody seen this before. Every layer encapsulates a single technical problem. For example, how to do the user interface, how to do the access to the DBase, things like that. And there are strict rules related to the pairing and coupling and generally communication between these layers. So usually only top layer can call the bottom layer, not from the bottom to the top. And that's why one way of splitting the code by this technical split. The second way of splitting the code is domain split, where the code is separated by the common functionality. For example, like on this example here, we have separate thing that do order processing, separate thing that do delivery, support, and things like that. And usually what we do when we decide to do this kind of split, we try to create a standard way for interfaces for these all things. So as a result, we are able to end up with standardized components, which separates a functionality by the domain. And the most explicit example of such split is a microservices architectural pattern, which, sorry, I didn't place here an example because it's a lot of drawing, but you can find it over the internet because it's a very popular way of shaping the architecture these days. So, what we do in Rockwell, how the Rockwell is dealing with splitting this code. Of course, we are using both techniques of splitting, so technical split and domain split at the same time. In general way, we can say that we use domain split to manage the middle level aspect of our software. For example, we are separating functionalities that is used on all our devices. And also we are using this domain split to separate functionality that is used on single devices. For example, let's call it an application level functionality. For example, things like that. Then we are using technical split to deal with the low-level aspect of our software. For example, abstraction of the hardware, abstraction of the operating system, abstraction of the file system. And as a result, we are transforming this ugly, chaotic monolith into something that is called a structure monolith. And this is what we have here. We're doing this by creating layers and creating components that separates functionalities. What is important to say about this stage of refactoring our code, that is very shallow refactor. Because what we do, we're just creating a new interfaces, components for old code. So we can see this here. Inside this component, this new shiny components, it's still the old code. And second thing which we do, we make sure that every single dependency which goes from the inside of the new component to the rest of the system is directed towards abstractions or other components which are very stable. For example, standard library. On top of that, we still have our old beloved legacy code inside these components. So at this moment, I think it's time to critique this approach, because one may say that, guys, all what you do is nothing more than wrapping this old code, worse or better, into new shiny paper. So just create a canvas which looks pretty nice from the outside, but the inside of this canvas still may not be much tasty. And yes, that's true. But even doing that, what we have is much better environment to create a new code, because new code need to interface only with these new interfaces. So it is much easier for us to create a new code, having the old code wrapped and isolated with the new components, with these new interfaces. And then, of course, we may go and take care about this old code, so do some heavy refactor or deep refactor in these components to make them better. But frankly speaking, in many cases, we will leave it as it is. Because right now, this code doesn't hurt us if this code doesn't have any bugs to be fixed. If the code doesn't need to be extended, then let it be. There are other things that we may spend the time and money, which could be more beneficial than fixing code, which right now doesn't make any trouble anymore. So let's take a look how this structure monolith supports the quality attributes we mentioned on the very beginning of my presentation. First of all, generally the monolithic architecture is always the fastest architecture that is able to operate on single CPU, single core. So for sure, this kind of approach supports the performance. Of course, it could be a little bit worse than this chaotic monolith, because now we have a lot of layers, a lot of boundaries to pass when we call some code. So it may work a little bit slower than this chaotic monolith, but still is the fastest option for single core. Then, as I have this reusable components, which has a standard way to be configured, create and configured, it's easy to me to reuse these components on multiple devices, and then it's easy to tune these components for the next device, which has different requirements to be satisfied. And then, because I have these layers, I have these components, I have this, let's say, architectural boundaries, it's easy to isolate the component I would like to test from the rest of the system, stop or mock everything else, and test it early. And finally, as I have the abstractions of the operating system, of the hardware, it's easy to move all the rest of the code to the new hardware, to the new platform, by just providing this lower level these modules which are and the layers which are on the lower level, and having intact all the rest. So for sure, I support portability. So looks like it works for us. Then let's take a look where we are right now with all these changes. And let's take a look on few fitness functions, and which are the architectural metrics. But before I will jump to it, I would like to add one disclaimer here. Previously, I mentioned that in the perfect world, if one wants to deliver the changes to the master branch, all these fitness functions have to be satisfied in order to deliver changes. But unfortunately, in real world, it's hard to expect that we will fix and change and improve this legacy code over the night. So it might be required that we will spend multiple sprints to improve this code. And there's no reason to keep these changes on the separate branch. We would like to deliver these changes partially. So we will be not able to satisfy all this fitness function at once or in the same moment. So it's possible that we will deliver the changes to the main branch, even if not fitness function unsatisfied. But of course, they still shall report the results to the developers, to the architects, so everybody knows that there is still more work to do. And then finally, when we will improve and fix this code, fix this legacy code, we may switch this fitness function into, let's say, you shall not pass mode, so no one is able to deliver the changes if these fitness functions are not satisfied. Saying that, let's take a look on the first architectural metric/fitness function, which we use in Rockwell. And this is named the refine interface progress. And what it says, what it shows us how much of our legacy code was already wrapped and packed into layers and components. So what does it mean? It means that this code has a new API, new facade. The sources is quite important and separate on two categories. The public, so the directory with the public headers that can be used from the outside, from the system, from the outside of the component, and the directories which is private, and the rest of the system cannot use these files which are only private for the component. And of course, it has to be documented over the web page, so every developer can go and learn by reading some documentation how to use this component. And what we see here, that's quite interesting, I would say. Let's take a look. This took almost more than half of year to improve us this metric by 10%. It gives a glimpse how much work it could take to improve legacy code. Of course, please remember that we spending only percentage of team's capacity to do this work. And then let's take a look on the second one metric. And this one presents us the how correct are dependencies between the classes from the perspective on this future architecture. And this metric shall improve only when we do the heavy and deep refactor of existing code. But even if we don't do this, which we don't do right now, as I mentioned before, but even if we don't do this deep refactor, we see that this metric still improves. And to get this metrics, we use the CPP depend. And as a result of this tool, we just not only have these numbers, but also we have this kind of diagrams to our documentation, this online documentation. And by the way, you can see that one of these dependencies is colored in the red because it's a not correct dependency. It shall be fixed by the changes in our code. What is important to see that there are two strange things that happened with this metric. One is here, this dip. It was caused by the change of the CPP depend from the one version to another. But more interesting is what is happening here, because we see that this metric is going down a little bit. That's because we have in our legacy code a piece of code that is, let's say, very popular. So a lot of other part of systems would like to use this code, but this code is not refined. So more we introducing a new code, which is fine. Unfortunately, more we using this not refined piece of code, so this metric goes a little bit down. But what I would like to say is that even if we are not focused on improving this metrics, so we don't do the heavy and deep refactor of our code, this metric still improves at least a little bit. So I think we are in the place when I can share a few practical remarks at the end related to the improving the legacy code. As you've seen on this first metrics, which showed that we had to spend half of year to improve it by 10%. Of course, we may say that improving the legacy code is a long journey. And these components and layers I mentioned before is just a first step. And do not try to take this journey alone. If you would like to improve the code in your company, build around yourself a group of supporters. Make sure that everybody in your company understands the importance of this improvement. Then make sure that every single developer understands this future architecture, this architecture that will support these quality attributes you would like to have. And then that every single developer understand also these architectural rules that guide the changes. And finally, this kind of work shall be common burden spread around all teams. But unfortunately, usually to make it happen, that this is a common burden and everybody work towards improving this, we need to have some agreement with the management to spend, for example, a percentage of team's capacity to doing these improvements. And percentage of the team's capacity is a time, and time is a money. So management need to be willing to spend the money to doing these improvements. And now the question is, what if management, for different reasons, just don't want to spend the money to do these improvements in the code? Then I would suggest, after all, to come with this future architecture that supports these quality attributes we would like to have. Then establish the architectural rules that will guide changes in the code. So new code will write according to these new rules towards this new architecture. And then establish these fitness functions that will check if a new code is created in the right way. At least we would like to freeze and stop at this technical debt at the level that we currently have. So do not let this technical debt to grow up. But if you succeeded to convince the management that it's worth to spend the money for improvement, then you have to be transparent to the management. So you need to come with some kind of metrics, as I showed you before, to show to management where we are now and what is the improvement. So they will understand they spending money in the right way, because they will not look into the code. They just will need to have some numbers that they understand. And again, as I mentioned before, this is a long journey. And do not try to fix everything at once. And do not be afraid of imperfect plans. So, because after all, it's better to have a good plan today than perfect plan tomorrow. And I like to say that software architecture is always an experiment. So you may do the changes in this architecture as you go. But the question is, so what is the difference between having this imperfect architecture, which I need to change as I'm going deeper, than having it as I have today? It's a very good question. And only one answer which I found in one book related to the software architecture. I do not remember which one it was. And the answer goes like that. Choose your architecture before the architecture will choose you. And I will add from my perspective, and will put you to the test. And finally, please remember about the Pareto principle. So sometimes improving 20% of issue in your code will cause that you will have 80% of improvement. For example, your time to market. And there are people who did research about this, so there are numbers to back up this thesis. So guys, that's all. Thank you for your time.